Hi everyone, I'm Rahul George. I'm a grad student at UC Riverside, and this is joint work with folks at Penn State. So I'm presenting OptiSan using multiple spatial error defenses to optimize stack memory protection within a budget. So like the previous talks have specified, memory safety is important. Specifically in our work, we focus on stack memory safety, and while not as prevalent as heap, it still persists. And over the past 3 years, we've seen that there are more than 200 stack CVEs with a severity score of 7+. And we find such vulnerabilities even in web servers such as Apache. So for example, here we have a vulnerability where an adversary can use a remote header to overflow a buffer on the stack and corrupt a lot of other data. So one way to find these potential memory errors is to use static analysis. So we could use value range analysis specifically, and you could find such potentially unsafe operations in Apache. And specifically for Apache, we find that there may be up to 3,000 such unsafe operations. And by an unsafe operation, I refer to a memory access that may go outside of the bounds of the memory region of the intended stack object. So a question that we try to answer here is, how do we best protect software? And what do I mean by best? So there are clear trade-offs between performance and exploitability or security. And here specifically, when you consider from the defense perspective, different defenses operate differently. So they may perform different operations such as metadata, checks, initialization, cleanup, as well as program specific, depending on how the program runs or the workload on the program. And in terms of exploitability, it varies from program to program with respect to the memory layout at runtime, as well as the accuracy of the defense to detect the actual memory error. So there are two classes of memory defenses, and which are well studied, and they differ fundamentally. So identity-based defenses basically detect whether the pointer may go out of bounds. The check is performed at point arithmetic. I think this is shown in the previous talk as well. And the metadata tracks the bounds of these objects. Location-based defenses, on the other hand, introduce invalid memory. And so the metadata tracks the state for this, whether it's valid or invalid. And the check basically functions by identifying whether this invalid memory is being accessed. In our work, we focus on Baggy Bounds and AddressSanitizer, as these are great cases, well studied, and AddressSanitizer is widely used right now. So in this figure, we try to illustrate the different operations that these defenses may perform. So on the left-hand side, we see the various operations that are in a program, such as stack memory allocation, pointer arithmetic, and the actual memory access. And on the right-hand side, we see the different operations that the defense may perform. So here the interesting point is that based on how the program is run, the memory access may execute more frequently than the pointer arithmetic. And what this means is that the AddressSanitizer check may end up being more expensive than the Baggy check. And then when you consider the entire program where you may have multiple such unsafe objects, multiple such pointer arithmetic instructions which may go out of bounds, and multiple such unsafe memory accesses, there are clear performance trade-offs to be considered. So our goal here is basically to model the defense overhead and to consider these trade-offs when we apply multiple defenses. And finally, to maximize protection by modeling both exploitability and performance. So the first challenge that we encounter here is, how do we model defense overhead at this operation granularity? So prior work, such as ASAP, looked at this in a very initial phase where they only focused on the check overhead. And so what ended up happening was that for some of the spec programs, they ended up going over budget. Similarly, a lot of recent work has been focusing on optimizing AddressSanitizer. And while great studies have been performed, they mainly focus on identifying the overhead for individual operations, starting from initialization, metadata, the actual checking. But our goal, on the other hand, is to identify the cost for, say, a single check for a given program. The second challenge is how to model the exploitability of a program. So let's say you have 3 potential memory errors. You would like to know that whether one should be prioritized more than the other. And the last challenge is to put all of this together to generate a defense placement considering both these defenses, as well as their performance implications, as well as the exploitability. And several cost-based approaches have been proposed, where they focused on applying a single defense using cost-based heuristics, wherein they would remove the most expensive checks, for example, until they hit the budget, or identify redundant checks in a very defense-specific manner. So our solution, or our basic idea is that since there are these clear trade-offs, we treat this as an optimization problem. So we model the cost of spatial memory error defenses, wherein we model the cost by modeling the individual operations that the defense may perform. We develop a formulation where the objective is to maximize the protection by modeling exploitability as well as considering the performance. And we develop an instrumentation pipeline wherein we're able to instrument the program specifically with considering the individual operations a defense may perform. And the right-hand side, we just highlight some of the formulae from our formulation, and you can find more details in the paper. So this is our framework. So starting from the top left corner, we use static analysis given the program source code or the bit code, and we identify these potential unsafe operations. We model exploitability by identifying the at-risk stack objects. And in the bottom left, we basically run the program to identify the individual check and metadata overheads. And combining the two of this, we feed it into a solver, and we're able to generate a placement for a given budget. We then instrument the program based on this placement to basically add defenses as computed. So here I'll highlight a few of the research questions that we've answered. There are more results in the paper. So the first and most important question is, does this combination of defenses help improve security? And more concretely, does it help cover more unsafe operations? And so across all the benchmarks that we evaluated, we see a maximum improvement of up to 52%. And the second question is, how are the defenses used together? We find that Baggy Bounds tends to be used more, around 85% of the time. And in the next slide, we'll see why. And the last part is that since we focus so much in performance, we want to evaluate the precision of our system. That is, given an input budget of 5%, how do we do? Do we shoot up to 10? So this first slide here is explaining the benefit of the two defenses. So we evaluated our work on the spec CPU 2006 benchmark, 17 benchmarks, and a few of the servers. And in these plots, from left-hand side to right-hand side, you'll see the coverage of these unsafe operations. The first plot, you see the coverage using AddressSanitizer alone. Second plot using Baggy Bounds. And the third plot using the combination of the two. And now coming to the usage of defenses. So as stated earlier, Baggy Bounds is used 85% of the time. And so there are two reasons for this. The first is the frequency distribution of the unsafe operations. So we find that most of these programs, based on the test suites that they provided, there is a positive skew in the frequency of distribution. And so Baggy Bounds tends to be applied to the cheaper cases and AddressSanitizer to the more expensive cases. Furthermore, as illustrated in the previous slide, there are cases where AddressSanitizer is slower, and Baggy Bounds clearly improves the budget required to cover all of the unsafe operations. This also leads to the performance trade-offs, and at various points you may see that the usage of the defenses changes drastically. And coming to the budget precision evaluation. So for 6 of these programs, we evaluate 3 budgets each. And since the budgets are program specific depending on the unsafe operations that the program may have, we evaluate 25% of the cost to cover all, 50% of the cost to cover all, and 75%. The dark region here represents the remaining budget, and most solutions were produced within 1 to 3 iterations. I'd also like to note there were a few cases where we went slightly over budget, but we're pretty close most of the time. That brings me to the end of my talk. Thank you for your time.